All right, as you can tell, I'm out today. However, we will do the same thing as normal. We are going to practice over the power rule for finding the equations for the derivatives or the tangent slope generators for functions. You will then quiz, and then the sub is going to play the next lesson. So we will start by practicing. So this is just a good example that takes into a lot of the power rule rules. I'd like you to find the tangent slope generator. Since this is y, you'd be looking for y prime. It's the same as just f prime. And go ahead and find y prime if y is this. I'm going to be going through the answers to these examples rather quickly. So if the sub could go ahead and pause and play the video when everybody's ready to see the answer and the work, that'd be great. But I'll go ahead and let you pause now, and when you play, I'll go over the answer. So the power rule, we take our exponent and we bring it down and multiply by the coefficient or just by anything. If there's nothing there, you just bring the 3 down, it'd be 3x. And then we subtract 1 from the exponent. So 4x cubed, its tangent slope generator would be 12x squared. 3x squared would turn into 6x to the first power. You do not have to write this 1 here. 2x's derivative is just 2. It's a line, a slope 2. So all of its instantaneous rate of changes, its tangent slopes would be that slope 2. You'd also consider using 1, bringing the 1 down and subtracting 1 from 1 to get you x to the 0. 2x to the 0 is just 2. Derivative of 1 is 0. It is just a horizontal line, slope 0. If I have the cubed root of x, I would rewrite this as x to the 1/3 and then use the power rule. I'd bring the 1/3 down. Subtract 1 from 1/3. That's like subtracting 3/3. And that'd be negative 2/3. I'd expect you for your quiz today to be able to rewrite this as 1 over 3x to the positive 2/3, just getting rid of the negative exponent. If you'd like to rewrite this using root notation, you can write it as 3 cubed root of x squared, as x to the 2/3 can be written as x squared to the 1/3. Okay. It also can be written as the cubed root of x quantity squared. However, neither of these are important. Just leave it as x to the 2/3 in the denominator for today's quiz. For the remaining ones, you would start by rewriting these using negative exponents so that they're in the numerator. So I'd have minus x to the negative first and minus 2x to the negative second. Using the power rule, the negative 1 gets brought down, becomes plus x to the negative second, which turns into 1 over x squared. And then here I'd bring the negative 2 down, giving us a positive 4, x to the negative third, which turns into 4 over x cubed. The 4 doesn't travel with the x. It's not being taken to the negative third power. It's just the x to the negative third, so leave the 4 in the numerator. Okay. Now, another problem, just to be aware of, is finding the derivative of f prime, the tangent slope generator for some function like this. I asked you to find the derivative of this. Important thing to know is that you do not know what the derivative of a quotient is, and students, when they err, they think that the answer is just that, but that's actually not correct. And we will learn how to do this using the quotient rule. However, even after we learn the quotient rule, you should probably do this the way we're about to do it, which is to simplify first. We should always look to simplify functions first, especially for today. And I would divide each of these terms by x, giving me x squared plus 2x plus 1. And then, using the power rule, I can find the derivative. So this would be the tangent slope generator for this function. I would not plug 0 into this, however, because if I plugged in 0, I'd have 0 over 0, which is a hole, so there's no tangent slope at 0. It wouldn't be 2. Okay, now to some applied questions using the power rule. We want to find the equation of the line tangent to this and parallel to this. Okay, so go ahead and start this problem. We can pause. I'll go over the answer. All right, so it's important to realize that, you got some x squared. I don't know exactly how it looks. And this solve for y is y equals positive 4x plus 3. So 4x plus 3 is, somewhere else. It's not the line that's tangent. But we want to find out, this line, wherever it may be, where it is tangent to the function and parallel to this. Okay? Now the key characteristic of the line that we need to find is its slope. The slope has to equal the slope of this line. It has to equal 4. So what I'm going to do is find the tangent slope generator for y. It's important to realize, okay, this, when plugging in x's, will give me the tangent slopes for my function. I want to know when the tangent slopes equal 4. So I just set up an equation where my tangent slope generator equals a specific slope. And I will solve for x to find the location where we'll have this tangent slope. And we find x is 5. So maybe if I go back to my original graph, maybe things are shifted over a little bit. So we'd be moving up at like 5. Maybe like that. And that's the slope. Okay, so, but regardless, that the sketch does not matter. So when x is 5, my slope of my tangent is 4, or we can just say f prime or y prime of 5 is 4. So if I want an equation of a tangent line, we first understand that this is the form of a line with a point and a slope. I know that the slope is 4. All I need to do is find the location of this tangent line, the x-coordinate and the y-coordinate. I have the x-coordinate. The x-coordinate is 5. I will need to find the y-coordinate 5. So that just means plug in 5 into my original function. To find the point, I got 25 minus 30. Negative 5 plus 2 is negative 3. So I have the point on the function 5, negative 3. The slope of the tangent at 5, negative 3 is 4. Here's my equation of my line. Okay, next problem. It's a tricky problem. Find k such that y equals negative 2x plus 3 is tangent to y equals kx squared minus 2. So in this situation, we have negative 2x plus 3 looks like this. And I need to create some parabola somewhere so that this line is tangent to this function. So it kind of appears right now, if I'm passing through negative 2, that my parabola needs to open downward. Okay, this is just by sketching. But we can understand that k can be anything. If we had a positive k, we'd be opening upward like that. The bigger the k, the steeper the parabola, the smaller, closer to 0, the wider the parabola. And it looks like we're going to create a situation like this. Now, we have to understand what is going on here. This is an important point because the line and the function share this point. So that means for some x, negative 2x plus 3 has to equal kx squared minus 2. Okay? The y's will be the same for a certain x. All right, so that's one equation, but I can't solve this for k right now. But the other thing that they share is a slope. The slope of this line, oh, this is not negative 2x plus 3. I'm sorry. So probably the same situation, but we're talking about negative 2x plus 3. So same situation, just better looking graph. And I'd be looking at that point, okay? Now, they share the slope. The slope of this line is negative 2. Well, the slope of the tangent to the x squared graph also has to be negative 2. So it's almost like I could take the derivatives of the two and set them equal to each other. Well, the slope is negative 2 from this line. The slope of this function will be given, using the power rule, by 2kx. Okay, so now I have two equations with two unknowns. I want to be able to try to solve one for a variable and plug it into the other, but I have two variables in both of them. So this is where we have a system of equations, and we can solve for a variable and use that to plug into the other. Now, I look at my first equation. I'm going to probably plug in this solve for a variable into this, but do I want to plug in for x or k? I'd have to plug in two locations for x. For k, only one location. So go ahead and you guys try to solve this situation to find x by solving this equation for a variable, substituting it in, and then finding what x is, and then probably finding what k is after that. Okay, so go ahead and do that. We can pause the video. I will go ahead and give you the solution. So solving for k, I would divide by 2x. I have k is equal to negative 2 over 2x, which is just negative 1 over x. And I'm going to plug that into my first equation, giving me negative 2x plus 3 is equal to negative 1 over x squared minus 2. Well, that right side can simplify to just be negative x minus 2. Now I have an equation with one variable I can solve. I can add 2x and add 2. And I get x is equal to 5. Well, if x is equal to 5, that means k is going to have to equal negative 1/5. It's cool to kind of see this graphically to make sure that we are correct. You won't be able to do this on your quiz. However, I can right now. If you're ever doing homework problems, using a graphing calculator can help you with your confidence that you're doing the right thing. So if k is negative 1/5, and we have x squared minus 2, will the line negative 2x plus 3 be tangent to that graph at a location? I feel like I'm off a little bit, because it should be at 5. 1, 2, 3, 4, 5. Did I type everything in correctly? I did negative 2x plus 5. That is wrong. It's negative 2x plus 3. And now I feel better. Okay, so that looks like a tangent line to that graph, so that worked out. Okay, so just remember, when you're encountering a situation like this, set up two equations, one where we have the shared point and one where we have the shared slope. Let's go to a piecewise function, making sure a piecewise function is differentiable everywhere. So this is another thing where two things must be true. To be differentiable, you must be continuous. So to be continuous, I can call this f little 1 and f little 2. It means this piece, f little 1 at 2, will have to meet up with this piece at 2. So one situation is make sure that the function's continuous. Make sure they meet up. Second thing that must be true is that the slopes need to be approaching the same value. So this is like the continuous, and this is like the differentiability part. Well, this is when our the derivative or the tangent slope at these points are equal to each other. So I can take the derivative of the top and the bottom at 2 and set them equal to each other. Okay, so this is the setup. You must understand this setup, and then go ahead and we can pause. You can solve and make sure you get the same answer as I do. All right, so plugging in 2 to get the continuity part, I get 2a plus 5 is equal to 4 times 3, 12 plus b. The second situation, the derivative of the top is just a. The derivative of the bottom is 6x plus 0. This is a very important. That b, yes, it's a variable. However, it's a constant, really. The variable is x, and we try to find this number. B is a number, so the derivative of a number is 0. So I have a equals 6x, but I don't really have a equals 6x because it's not 6x. This is the derivative of x. I want to find the slope of the tangent to f2 at 2. I plug in 2, I get x is equal to 12. Sorry, a is equal to 12 after x is equal to 2. Knowing that a is equal to 12, I can now find b by plugging in that. I'll get 24 plus 5 equals 12 plus b. 29 equals 12 plus b. 29 minus 12 is 17. So I get a is 12 and b is 17. Okay, so plugging that into this piecewise function will ensure that the two pieces meet up and the slopes would be approaching the same value. Okay, last question. Talking about position, velocity, and acceleration. We have a position function of an object. What is the exact velocity and acceleration? So at the end of the video in the first lesson, we talked about, position, velocity, and acceleration. And let's just start with, the third part. I asked you to find the exact velocity and acceleration of the object at t equals 1, and what is the average velocity at t equals 1. Well, we know that the average velocity is just the change in my position over the change in time. And that's just slope of position. Okay, so let's go ahead and find my average velocity from 1 to 2. I'll find my position at time 2. So that's 8 minus 8, which is 0. Minus my position at time 1. 1 minus 2 is negative 1 over 2 minus 1. So I get an average velocity of 1. Okay, good. Notice I use slope. Okay, so if I want to find an average velocity, I just use the slope of the secant line of position. Slope of secant. But what if I want to find the exact velocity and the exact acceleration of the object at t equals 1? Well, to change this from an average velocity to an exact velocity, instead of finding an overall change, I'll find the instantaneous change. So that's a kind of a Greek D symbol there, which means to find the exact velocity, I'm going to look at the slope of the tangents of x of t. And that creates this nice little kind of one leads to the other thing, which is going to be used often. X prime of t is equal to v. The slopes of the tangents of my position function will give me my exact velocity. If I want to look at acceleration, well, average rate of change of velocity gives us average acceleration. The exact acceleration will just be given by the slopes of the tangents of velocity. So if I want to find the exact velocity and the exact acceleration, I'll just take the derivative of my position to get a velocity function. I'll take the derivative of my velocity function to get an acceleration function. Why don't you go ahead and do that? check your answers with a neighbor while I do the work. So x prime is equal to v, which equals 3t squared minus 4t. V of 1 is equal to 3 minus 4, which is negative 1. A of t, which is v prime of t, would be 6t minus 4. A of 1 would be 6 minus 4, which is 2. Okay, so rates of change of position gives us velocities. Rates of change of velocity gives us accelerations. Okay, that's it. Let's go ahead and take our quiz now. You can clear your desks. Sub will pass out the quiz. When you're done, place it in your box like normal. Get out your notes, and the sub will play the next video on the product and quotient rule for finding tangent slope generators. Thank you. See you guys on Wednesday.